We're not 6-1, but we're close enough, so we're starting off on a new topic. So we're going to talk about control volumes. And we kind of have talked about control volumes, and I'll illustrate to you the fact that we kind of have. Let's take an example that we've talked about, say a weir, right? So you have flow like this. No, I don't want to do this. So what we've done, so this is a weir, and we have flow going over the top, and what we've done is we've said that if we take a streamline, we can define the behavior at 2 points on that streamline. Of course, we could take another streamline, and we've kind of done this, if I can draw this properly, and we could do the same thing. And we could isolate the portions of that streamline, those two streamlines, and we know something about them, right? We know that along a streamline, the flow is along the streamline, and the flow normal to that is 0. And so what this means is that this is kind of a bounding surface, and that all the flow inside here is, well, we've done it, V1 A1 is equal to V2 A2, which is just the flow through these systems. So we haven't explicitly talked about control volumes, but in some way we've kind of included it in what we've been doing. But certainly the volume between streamline, or the area between streamlines, or in 3D the volume between stream planes, I guess they would be, is the control volume that we would like to mess around with. And so what matters in all of this is that we can try and think about this. And so I won't play it again. You saw it. Let's see if you get this. So let's see if this will run. So this isn't completely esoteric. There's some error occurred. Yeah, I guess it had some remnant material stored, right? So it just needs to refresh. So I can do that. Well, you saw the beginning of this. Could not load shockwave fresh. Don't know why I can't do that. Looks like it might work now. Very rousing. So, screaming and you're on a train, then you hear your scream, it doesn't change pitch. If you're screaming and someone's standing off the train, then it changes the pitch and you go past. So to do that, we need to first of all figure out exactly what control volumes mean, to look at the relevance of kind of static and moving control volumes. So the simplest way I can to be able to illustrate these different points are to look at these three different kinds of control volumes. So one is fixed and non-deforming. So fixed and non-deforming means you have a pipe, and in that pipe you put an upstream location and a downstream location, and between those it isolates a volume which doesn't change volume. The control volume doesn't change volume, and it doesn't physically isolate. So maybe when fluid comes in one side, it goes out the other side. Control volume control volume that is non-deforming and moving would be one which is a jet engine. Jet engine hopefully doesn't change its size. Relative to you, if you're sitting here observing the left-hand side of the plane, it's underneath you, hopefully it doesn't go relative to you. It does go into something like sitting right. So it's physically moving in space, but it's actually not changing in space. Of course, the example flips around the room. Not only does it change in size as it loses air because the pressure is pushing it out, but also it moves location as it flits around. So those are the three kind of component behaviors that we'll look at. This obviously is the simplest, and it gets progressively more difficult, more challenging as we go down the chart. And so what we can do is we can look at an example that might illustrate that. And so an example that might illustrate that, the best one I can think of is this. So let's look at some pictures. So wireline logging. So if you work in petroleum industry, the environmental industry, wireline logging is what's usually done with most oil holes, gas holes, sometimes in environmental monitoring holes as well. And that is that you drill a hole. If you drill it with a method that doesn't take core, you have no idea what's in the hole at all, because you just end up with chips coming out of the top of the borehole as you drill. And so you'd like to know what the stratigraphy is. So there are a couple of ways you could do it. You could send a borehole camera down to look at the walls and to map fractures and stuff as you go down. Or you could send a wireline tool down, which would monitor something else. And you could monitor all kinds of different signals. The signals and examples of these would be basically a sonde. And pictures of these sondes are exactly this. So they would have some measuring device that's in here. They might have some calipers to keep it pressed against the hole or central in the hole. And it would measure things like temperature with depth. It would measure a little spinner log as an impeller to look at flow along the hole, so you can see stuff where it's coming into the borehole and zones where it's going out, because you know those are permeable zones. It might measure gamma ray counts as measures of whether you have shales as caprocks in the rock or as part of a reservoir. It may have an active neutron source in there, cesium-37 to be able to look at neutron backscattering, to look at porosity and water contents, all kinds of things. It's really quite sophisticated. And of course, it's companies like Schlumberger, the French brothers, who've basically made their fortune by inventing these ideas for downhole logging. And so an example that we could look at is basically to look at reference frames, and what comes out of it is some kind of log, and the log would be measuring porosity change with depth, fluid velocity change with depth, gamma ray count, which is analogous to the amount of shale or clay in your rock with depth. And it's really quite a sophisticated analysis that can be applied to this. But it's useful because, in our particular case, because it's something where there's kind of a moving frame of reference. And so all this is done is it's lowered down the hole on a cable, on a winch, shot down to the bottom, shot back up in real time. It's not stopped at individual locations, it just measures as it's physically going down the hole. And so So that is what happens in these systems. You might get an easy class. I see that 17 minutes left on the battery, but let's see how that goes. So, so let's look at what we might want to do with that. So let's take logging. So this is the idea. So you have the ground surface. And we go down with depth. Let's call this, as we have done, minus z. Let's call this plus z for elevation. And we're going to measure some parameter as we go down with depth. So the easiest one is to take a scalar value. It could be pressure, or it could be temperature. Let's use temperature, just because there's a geothermal gradient, and the geothermal gradient is equal to something like 25 degrees C per kilometer. So start off at 0 temperature. Well, we're not at 0 here, not at 0 centigrade, but close enough. And so let's take this as temperature. And so what we'd like to do is we'd like to attach ourselves to this thing that's going down here, this measuring sonde, and we'd like to figure out what the change in temperature, dt with time, is. And so this is the substantial derivative. We've kind of used this before, although we've not really said it. And so the substantial derivative is something that we could write as change in temperature with time plus the change in temperature with time. And we could look at how this changes as a function of the coordinates of our 4D world. 4D world is 3 coordinate systems and time, x, y, z, and time. And so we could write this as multiplying by dt over dt. Of course, that doesn't do anything for us. We could do it as change in z, change in the vertical direction. And if we do that, then this temperature change with time is what we're going to see if we're attached to the sonde. So this is attached to the sonde, S-O-N-D-E, and it's going to be equal to how the temperature changes with time plus, what's this parameter here? This is the velocity in the z direction. So velocity in the z direction times the rate of change of temperature with the z direction, not time. Okay? So let's think of what this is. So what does this say? This is temperature is equal to 25 degrees C per kilometer times kilometers, right? And so what we need to do is be able to figure out exactly what this dt dz is. So I guess it's actually, what is it? dt dz. We can just divide both sides through by kilometers, right? That's the change in temperature with depth, which is going to be equal to same units as this. So is that true? Well, kind of, right? So the coordinate system is positive up, and our temperature increases as we go down. So I think there should probably be a negative in there, right? So as you decrease in elevation, the temperature goes up. So what we could do is, if we're going down in the sonde, we'd like to know what the temperature change is. Then if we're going down at a velocity of, you choose it, Vz is equal to 1 kilometer, let's do hours because it seems better than a second, right? So you choose a velocity. It's downwards, so this would be negative 1 kilometer an hour. And so if we put it into this, what do we end up with? This is not changing in time, so we're looking at this, and this profile exists now, it exists in 10 minutes time, it exists in an hour's time, it hasn't changed in time, so this term here is 0. And what is this term? The velocity is equal to minus 1 kilometer per hour times this value here, which is minus 25 degrees centigrade per kilometer. And so the relative change in temperature as we went down would be equal to 25 degrees C per hour at that particular velocity. So that's all a substantial derivative is. It allows you to be able to figure out exactly what you feel as you're going down in the elevator along this sonde as a function of the conditions that are static and not changing, and maybe as a function that they're changing. So this would be down. If we went up, what would it be? It would be equal to, again, 0 minus. Well, no, sorry. It would be 0 plus, but now this velocity would be equal to plus 1 kilometer per hour times minus 25 degrees C per kilometer. Okay, so it wouldn't change, right? So that's really all a substantial derivative is. It allows us to tell us what we feel as I go across the room as to what the conditions are in space. And we've kind of used it before, right? We talked about Newton's first, well, let's get to that in a second. What else could we do? So what the requirement for this so far has been that this distribution has been static with time. What happens if we change it so that a line parallel to this moves so that the temperature change dt, the change in temperature with time, is equal to 1 degree C per hour. And so in other words, we start out going down here, and the temperature here is equal to 0. But while we're going down here, this whole curve moves by some small amount in this direction, right? So that's what really this is saying. And so that would allow us just to put this extra magnitude in here, and you could do the calculation for that. In this case, it's increasing with time, and so the rate of change, what would it be? So if we're going down again, then the change in temperature with time that we'd see would be equal to this, which would be plus 1 degree C per hour. We're going down, so it's equal to plus this term here. The velocity is still negative, so it's minus 1 kilometer an hour multiplied by minus 25 degrees C per kilometer. So my handwriting is getting even worse, but you get the idea. And so that's really what substantial derivatives are, and they're kind of important. So reference frame is important. This isn't changing. In the first case that we did, the temperature isn't changing in space, but because we're moving, we see a temperature change occurring. Well, it could be your lucky day. And so we can use that to be able to figure out exactly what that is. So substantial derivatives, this is a substantial derivative, and it allows us to be able to look at different frames of reference. Okay. We've kind of seen this before, so what we've done so far is a value for a scalar. Have we seen it before? Kind of, right? And we've kind of dealt with it before. So we know that in solving Newton's second law, which is important in Bernoulli, we can write this as sum of forces is equal to mass times acceleration, say in the z direction, which we've also written as mass times, we should have written it as dv dt. And we can, let's not do that. Let's write it just as the way we've done it. Mass times change in velocity with time. And we know that we can also multiply this by what? By 1. We've done it. Which allows us to be able to write this as mass times change in velocity with location times dz, I know my z's and t's look the same, change in location with time, not z. So what's this? This is just velocity. So we have exactly that expression that we've used before, and the physical meaning of it, so this is this, which we've also written as what? So all of those are equivalent. And so we don't need to get wrapped up in the math of it, but basically what we're saying is that you can change it from something that's written in terms of time, so in other words, mass times change in velocity with time. So this is what I see. If I'm the guy doing the accelerating, I change velocity with time, and that's what's going on, and the forces that have to be applied to my body have to respond to that, inertia forces. But if you're looking at this, you can also look at my trajectory as I go across the room and just see how my velocity changes, not with time, but in space as I go in front of you. And that gives you the ability to be able to still calculate the same forces, because obviously those forces which are making me accelerate that I feel have to be the same forces that you would calculate if you're looking at me from your reference point there. That's really all substantial derivatives are. So it's important to be able to make that connection in what we do. And so we have seen it before in what we've done. So let's do a couple of things. Well, let's close out just with this comment. So what we've done is that we've talked about substantial derivatives for scalar systems. So let's just write these out. So it's 6-1. So substantial derivative, or sometimes called material derivative, and this is important because it revolves around frames of reference. So if we look at a scalar system, and so it could be, for instance, the change in pressure with time. Then if we did that for all the components that we want, then what we do is we just do this. Change in pressure with time plus change in pressure with time plus change in pressure. It gets boring after a while, right? With time plus change in pressure with time. That's the last one. And so what we could do is we could multiply by 1, dt, dt. So our world is four-dimensional, right? X, Y, Z, and time. And so we're going to multiply by time divided by time, x-coordinate divided by x-coordinate, y-coordinate divided by y-coordinate, and the change in the z-coordinate divided by z. And so this we don't care about, right? This is going to be change in x with time. In the book they call this the velocity u, which is, we call it vx, I guess, depending on your terminology. This would be the velocity in y, which they call v, and this would be the velocity in z, vz, which in the book they call w. And so those are what substantial derivatives are. If you look at a vector, which is equal to, for instance, a vector would be F equals ma. Mass is the mass of this. It has no directional properties, but this would be forces in the x direction and y and z. So we could also write this out as the force in the x direction, force in the y direction, force in the z direction is equal to mass times the acceleration in x, y, and z. Because we have to resolve in those three different locations. So this is just a way of writing this. So you could do the same to calculate what so this is a vector, so underscore means a vector in this particular case. And you could do the same kind of analysis to figure out exactly what this substantial derivative would be if you're trying to look at rates of changes of velocity. So this would be the same as, it's getting too complicated already, right? But this would be something like dv, which is a vector, dt, And this vector here is going to be velocity in the x direction, velocity in y, z, and z, right? And I won't derive those, but you can, I'll let you look at those and get those down. So, so you can imagine that if you look at that, you end up with a kind of a complicated vector arrangement, which we won't really use very much, but you should realize that it makes a difference when you're dealing with a scalar, something that has magnitude but not direction, and a vectoral quantity, something has magnitude and direction. And if you look at those, and you can see these for yourself. We've gone through this, we've gone through this, we've gone through this, we don't need to go through this. This is what it would look like. So you have those in your notes. So there's a difference between when you do it with a vectoral quantity, a tensor, which is acceleration, and a scalar, which would be pressure or temperature, as to what these things look like. And there's a quick example that you might try to just see that you understand what's going on with these. Our final goal, really, and the reason this is important, is that rather than looking at this behavior in this kind of Cartesian coordinate frame, what we could do is we could come back to this idea of streamlines, and we might want to calculate what the accelerations are along these streamlines, both along the streamline and normal to the streamline, using the same concepts of frame of reference. And so what we'll do next time is we'll talk about an along streamline acceleration, because this is the acceleration that basically is the part of Bernoulli that we need to accommodate. But the main part for what we need to do today is realize that there are actually different frames of reference that you have to worry about. And the different frames of reference should always give the same result. So the forces acting on me, accelerating me, are always going to be the same forces, and you should be able to calculate those whether I'm seeing what velocity I'm moving at and what acceleration I'm moving at, or you in a static frame of reference are seeing me go in front of you. You should be able to calculate the same forces. And that's basically what the idea of these control volumes are. And so next time we'll talk a little bit about accelerations, and then we'll do the simplest case of looking at a static control volume and seeing how we accommodate mass in, mass out. Okay? Thanks very much.